In this video, we're going to use the equations we've just worked out to look at what happens to electric field and charge inside metals, in particular inside holes in a conductor. So let's start off by assuming we have some blob of metal or some other good conductor, and let's put a negative charge over there and a positive charge over here. Now we know that what's going to happen is the negative charge is going to attract some positive charges to the surface over here, and the positive charge is going to attract some negative charges to the surface over there. But could there be any charge in the middle? Could there be, I don't know, a bunch of positive charges over here or negative charges over there? Well, what we can do is we can do our surface integral, Gauss's law. We can pick a region inside the metal. Any region inside the metal. Now what we know is that if you're in a conductor, you can't really have electric fields when things are in steady state. So if you had a conductor and there was an electric field, then the positive charges would move and the negative charges would be left behind, or vice versa. And they would keep moving until there was no electric field left over. Because there's nothing to stop the charges moving, if you have any field, they will move until they cancel it out. So what we know is that as the surface is entirely inside the metal, there can't be any electric fields there. Therefore, the surface integral of the electric field dot the normal vector dA is going to be 0, because these are all 0. 0 times whatever that is going to be 0. But if you remember, Gauss's law told you that that was the amount of charge inside, divided by epsilon naught. So that means there cannot be any charge inside. So we have to rub it out. And as we can draw such a surface anywhere we like, we can draw it over here, we can draw it over there, draw an overlapping one like that, and for any one of them the charge must be 0. That's telling us that there can't be any charges, unbalanced charges, anywhere inside a perfect conductor. Okay, well that's pretty cool. But now let's make things a little bit more complicated. Now let's assume that we have some randomly shaped conductor, but now it's got a hole inside it. And once again, let's bring, let's say, a negative charge over here. So that will produce some positive charges along here and some negative charges along there. Now we know there's no charges anywhere inside the metal, but could there be some charges on the surface around here? So like you could imagine that you might end up with some negative charges here and some positive charges over there, for example. Could you have something like that? Well, what we can do, once again, is define our Gaussian surface. So in this case, let's pick a Gaussian surface that's just outside our hole. Now once again, because the Gaussian surface is entirely going through the metal, there can be no electric fields inside the metal. So that's telling us, once again, that the surface integral E dot n dA equals 0. So there can't be any charge inside this hole on average. So the hole can't have on average a positive or a negative charge, otherwise there would have to be an electric field, and we know there isn't. But it doesn't tell us we couldn't have, for example, positive charges there and negative charges there. All it tells us is the total charge inside on the surface of the hole must be 0. To find out whether you can have charges positive and negative here or anywhere else, we have to use the line integral. So Kirchhoff's second law, the incomplete version of Faraday's law. So now let's do a line integral, and we'll have a line that goes like this. So it goes from the positive charges to the negative charges, and then goes around through the metal and comes back again. So now let's look at the line integral along here of the electric field dot dl. Now inside the hole, there's going to be electric field. In this case, you've got positive charges here, negative charges there, so there's going to be an electric field. So that integral along there is going to be positive. How about this part of the line around here? Well, that part of the line, there's no electric field, so that's going to be 0. So what that's telling us is we go up in voltage, and then nothing. So we got a non-zero integral there, and it's 0 around there. So if there was charge inside, that would not be equal to 0. But that violates the law. We know that it must equal 0. So what's going on here? That tells us that there can't be charges anywhere on the surface. There can't be positive charges or negative charges here. So in fact, there can't be any electric field inside the hole, which is kind of cool. So we now know that there's no electric field and no charges inside a metal. And even if you have a hole inside the metal, there's no electric field and no charges on it. Okay, so we're definitely getting places here. But what happens if you put a charge inside the hole? So let's imagine now we have a chunk of metal, and once again we'll put a negative charge outside, and it has a hole in it. But now we can put a positive charge inside the hole, smuggle it in somehow. Now what's going on? Well, once again, pick our Gaussian surface. Let's pick a Gaussian surface just outside the hole again. So once again, the surface integral around there is 0, which means there can be no net charge in there. But we know there's a positive charge in there. How can there be no net charge? Well, clearly there must be a negative charge equal and opposite to the central positive charge around the inside, because it can't be anywhere else. So if you do put a charge in a hole, there's an equal and opposite charge immediately around it, and nothing else. So this gives you some sense of how powerful these techniques are. This is also enormously practically useful. This is the concept of a Faraday cage. What it means is, forgetting about the charge here, if we have a complete surface of metal around you, then no matter what electric field is applied on the outside, there will be no charge and no electric field on the inside. This, for example, is why you're pretty safe if you're inside a car when it's struck by lightning. There's enormous electric fields and charges going all around, but they'll all be running around the surface of the car. If you're inside a complete bit of metal, it turns out that even if there are gaps in the metal like windows, you're probably still fairly safe. There's no electric field inside.